Welcome everyone. For today's prep, we're going to start to look at geometric series. So in class, we were looking at geometric sequences, and now we're going to attempt to see what happens when we try to add all those terms together. So let's look at our geometric series, and let's just revisit what the original sequence is, our geometric sequence. All right, so our geometric sequence. So the general form here is some constant a times some constant r, and that constant r is getting raised to the power n. So a and r here are just constants. And let's suppose that we're going to start our sequence. The starting index is going to be n equals 0. So the very first term, if we write out the first few terms of this geometric sequence, very first term is going to be a, and then the next term will be a times r, and then the term after that will be a times r squared, then a times r cubed, and so on. And it just keeps on going. So what happens as we go from term to term? Well, if we're looking, as we go from this very first term to the second term, we multiply by r. And then as we go from the second term to the third term, what do? Multiply by r. So to get each next term in our sequence, we're just multiplying by an additional copy of r. And this just keeps on going. So that type of behavior, when it's kind of this repetitive multiplication, that's an exponential function. So if you remember, these geometric sequences really are related to our exponential functions. All right, so if this is our geometric sequence, well then the geometric series is when we attempt to take all these terms and add them all together. So we try to do this infinite sum here. And the way I have the formula written here is the starting index is n equals 0. But another common way to write a geometric series, so we'll sometimes see this as well, is to have it start at n equals 1. So you might also see this written as the series from n equals 1 to infinity of a times r raised to the n minus 1. So that accomplishes the same thing. So the starting index is 1. We just got to shift our exponent there a little bit. All right, so we're going to be looking at geometric series. These are going to kind of pop back up here and there as we kind of investigate further into series and then later on power series. And it turns out geometric series are a very special type because we actually have a really good idea of what's going on with them. We actually can figure out the sum quite easily. So we have a nice little formula that tells us what the sum of this infinite series is. So if we have this geometric series, the sum is the a value divided by 1 minus r. So this is kind of special. So we're going to be dealing with series quite a bit. And in most cases, when we just have a random series that we're investigating, we're not going to be able to figure out the sum exactly, be able to estimate if we add enough terms, that kind of thing. But we're not going to have such a nice little formula like this that tells us exactly what the sum is. So geometric series are very, very special. And whether this series converges or not, whether this sum exists, depends solely on the value of r. So if the absolute value of r is less than 1, then our series converges, and then we have this nice sum formula. If the absolute value of r is greater than or equal to 1, well then the series diverges. So the sum doesn't really exist. It's undefined. All right, so let's try an example. Let's try 2 examples. So we're going to figure out whether part A and part B, whether these two series are convergent or divergent. And if they're convergent, we're going to figure out the sum. All right, so how does this work? Well, whenever we're presented with a series and we suspect it's geometric, the goal is to kind of get it into that geometric form. So let's just write that to begin with. We want to write this as a geometric series, and the general form here is a times r raised to the n equals 0 to infinity. And then if the r value satisfies the condition, we know what the sum is. And we'll actually prove this result later on. We're not going to prove it right now. Right now, I just want to get a little practice working with these geometric series. All right, so let's keep in mind. So when we're trying to, when we have a series like this, we want to figure out the a value and the r value. And so we try to write it out in this format. So if we're looking, if we match up, let's look at the first one. We've got this sum going from n equals 0 to infinity. We've got the constant 5, and then we've got the exponential part, 1/2 raised to the n. So if we match things up, we see that the a value is just this constant in front that's really not part of the exponent here. It's kind of off to the side. And then the r value, that's the exponential part. That's the base of our exponential. And if we look, that's what this 1/2 is doing. So the 1/2 is this number that's getting raised to the n. And that's what we see here, r raised to the n. All right, so the a value, if we're matching things up, the a value we see is 5, and the r value is 1/2. So that's enough. We have it written in this geometric series format. Really, there wasn't any work to do. And this is enough. So we can say that this is a convergent geometric series Let's state the r value, r equal to 1/2, and let's state the necessary inequality, satisfying absolute value of r less than 1. So this is the type of explanation that I want to see when we're claiming that a geometric series is convergent or divergent. So state the conclusion, either convergence or divergence. State the name of the series, what type of series it is. This is a geometric series. State the r value that you have, and then state the inequality that shows you that it's convergent. Or if it's divergent, state the inequality that shows you it's divergent. All right, so we have our explanation. We know this is convergent, so that means this sum formula actually works. So if we fill in, the a value is 5. So we're in our sum formula, we're going to replace that a with 5. And then the r value is 1/2. So we're going to replace that r with 1/2. And if we do the arithmetic, we end up with 5 over 1/2, which is 10. So that's the sum of this infinite series. All right, let's try it again. Let's try another one. So let's look at part B. So this one is not immediately, it's not as nice as that first one. So it's not immediately in that form. We want to get it into this form a times r raised to the n, and this is when n is starting at 0. So if we look, what's the issue with this one? Well, n is starting at 0, so that's good. But if we look at our exponent, it's not just raised to the n. There's extra stuff here. So if our index is starting at n equals 0, that means we need our exponent, it needs to be just the n. All right, so we've got some extra stuff here, some extra factors. So we first have to rewrite this series. Right now, it's not immediately written in the correct format for us to use our sum formula if it comes to that. So how can we do this? Well, we need to get it so that it's raised to the power n. We've got one extra copy of 1/2 that's getting multiplied in here. So let's break that off. So let's peel off that extra copy of 1/2. And let's put it in front. Just like that. So again, if we multiply these together, I have one copy of 1/2 times n copies of 1/2, and I can just I can add together the exponents, and I go back to what I had, so the n plus 1. So this expression is equivalent to this expression. But this expression is now the format we need. So we've got the a value, and then we've got our exponential part, so we can figure out the r value. So in this case, the a value is 1/2, and the r value is 1/2. So now we have enough info to figure out if this thing is going to converge or diverge. So let's state our result. And we see that the r value is 1/2. So we can say this is a convergent geometric series. Let's state the r value. So r is equal to 1/2. And let's state, again, the necessary inequality that we need to make this conclusion. So the absolute value of r is less than 1/2. So again, when we're doing these, there's kind of a few things that I want to see in your explanation. It doesn't have to be a super long explanation, but I want to state the conclusion, state the name of the series, so this is a geometric series, state the specific r value that we're working with, and then the necessary inequality. So we're looking for those 4 things. And because this is convergent then, we can actually figure out what the sum is. So the a value is 1/2, so that'll go on top of our fraction here. And then we get 1 minus 1/2. So the a on the top, or the 1/2 on the top, that's our a value. And then the 1/2 in the denominator, that's our r value. And if we simplify that, we end up with 1. So the sum of this series is 1. All right, so we're going to get a little bit more practice in class of kind of working with, kind of massaging these series so that we get them in the correct format. So we'll see this one in class, but you can tell it's not immediately written in that a times r to the n format, so we're going to have to do a little bit of algebra to get it there. So we'll see you in class. Bye-bye.